Thank you very much for inviting me to give this talk. I will share my slides. So I think you can see my slide now, my first slide. Okay, good. Okay, yeah, so again, thank you for inviting me to give this lecture, and I will talk now about the knowledge gaps towards creating real synergy in plasma catalysis, and what we can learn and how we can get new insights by experiments and modeling. And this is work that was done in collaboration with some people in my group, but also with Kevin Rauwenhorst and Leon Lefferts from University of Twente. Maybe because I don't know whether all of you are so familiar with plasma. So first, a brief introduction. Plasma is a partially ionized gas. It's also called the fourth state of matter. So if you have a solid material and you heat it, you will get a liquid. If you heat it further, you get a gas. And if you would heat it further, you get a plasma, which is a partially ionized gas. So you can see here, there are free ions, free electrons. Now, in this case, this can be by heating, but it can also by bringing in other energy, so electrical energy. And that is actually what we do and what is done in plasma catalysis. And because the electrons are so much lighter, most of the electric energy goes into the electrons, and they can then dissociate inert molecules like CO2, nitrogen, methane, so that thermodynamically unfavorable reactions can take place at mild conditions, so there's no extra heating of the gas needed. Why is plasma then so interesting for gas conversion? As I said, it allows efficient breaking of the molecules because the electrons activate the molecules, and you see here a vibrating CO2 molecule. You can imagine that this vibrational excitation easily leads to dissociation. So this is the most efficient dissociation pathway. Now in plasma, there is often, certainly in plasma catalysis, non-thermal equilibrium, which allows these reactions to happen in an efficient way. So it opens alternative reaction pathways at lower temperatures. Now, plasma is actually, it allows a flexible feedstock, and it breaks up the feedstock into its elementary species. So this includes CO2 with wide opportunities for waste streams, and it can have even benefits to have nitrogen present up to 50%. And so often in emissions, there's a lot of air or nitrogen present. But we have seen even that this can even help to improve the CO2 conversion. But you can also combine CO2 with a hydrogen source, for instance, methane. Then we have dry reforming of methane, or hydrogen. Then we have CO2 hydrogenation, or water. So we can call that artificial photosynthesis. Or a nitrogen fixation to ammonia or to NOx for fertilizer applications. Also methane coupling to ethylene, for instance, or for hydrogen synthesis, ammonia cracking for hydrogen synthesis, and so on. So there are many possibilities that can be, many reactions that can take place and that can be used in plasma. And of course, this also allows flexible products. So if we have CO2 and methane, then we typically produce syngas, and we can tune the ratio depending on the CO2 methane ratio. We can also directly form C1 to C5 hydrocarbons, oxygenates, green hydrogen, and so on. Now, I think the biggest advantage of plasma is that it uses electricity, as I already said, and it quickly is switched on and off. So it is very suitable for the combination with renewable electricity. So it can allow production on demand also at smaller scale. So it also has a continuous flow, as you can see here, a certain plasma reactor, and you bring in the gases, for instance, CO2 methane, and you produce syngas, or methane or ammonia, and you produce green hydrogen. and the residence time can typically vary between milliseconds to seconds. You can see this is a very simple reactor. This is just a quartz tube here, so no rare materials are needed, and because it's a simple design, it also has a low capex. Now, upscaling can be done by numbering up, so by placing a large number of reactors in parallel, and this was already demonstrated many years ago for ozone synthesis. So this was with dielectric barrier discharges in parallel. So this allows then also delocalized production, for instance, for fertilizer production by local farmers based on a few solar panels or a windmill. Now, the biggest disadvantage of plasma is that it's not selective. So it's very reactive, but therefore not selective. So therefore, it is interesting to combine it with catalysts, and that gives us plasma catalysis. Now, there are two main configurations. First start with the one that is maybe the less being investigated, which is post-plasma catalysis, where we work with a warm or a thermal plasma, so very high temperatures, like a gliding arc or microwave plasma. And then the catalysts are placed, as I said, post-plasma, and they are thermally activated by the hot gas coming from the plasma reactor. And then there is in-plasma catalysis, which is typically done in a non-thermal plasma, where the temperature is just slightly above room temperature. And then the catalysts can be placed inside the reactor. And that is typically done with dielectric barrier discharges. I give an example in a minute. So then this allows a direct interaction between the reactive plasma species and the catalyst. So you see here, this is just a plasma. You see here filaments. This is post-plasma catalysis, and this is in-plasma catalysis. So this direct interaction allows more possibilities for synergy between plasma and catalyst. So this shows an example of a typical in-plasma catalysis configuration. You see here a tubular DBD. This is a packed bed DBD. So we see here, so here we have an inner electrode. Then we have a quartz tube or alumina tube, so a dielectric tube. And around this, there is another electrode, which is wrapped around this dielectric tube. So, and the gap between them, which is typically a few millimeters, is filled with beads, which are typically also like 1 millimeter or 2 millimeter. And they can be coated with catalysts. So these beads are typically dielectric. Here you also see, I will just stop my pointer so that I can open. Yeah, okay, I think it's not working, but here you saw streamers inside inside a plasma. So this is a side view, and this is top view, how it looks like. Now, of course, if you put a catalyst inside the plasma, this gives a lot of complex interactions. And we list here a few. This was from a paper that we published 2 years ago. So you can see there are actually also a lot of physical effects. For instance, as I said, this packing is typically dielectric, and that changes the discharge type from local discharges to surface discharges depending on the dielectric constant. So as you can see here, this is a local discharge between the beads, and this is more a surface discharge. And because of the dielectric beads, there can be electric field enhancement due to polarization of the beads, which then causes electric field enhancement. Now, the beads are typically coated with a catalyst. So, and you can see here, this can also change the discharge from filamentary to uniform plasma, and I will show examples of that later in my talk. And this can depend on the synthesis method. So this is also something that needs to be carefully understood. And of course, these are physical effects, but they change the plasma conditions, and thus they also change the plasma chemistry. Then catalyst pores, catalyst supports typically have pores. Then the question arises, can plasma penetrate inside the pores? And if not, can species still diffuse into the pores? I will also come back to that later in my talk. And then there are, of course, also chemical effects like reactive species that reactive plasma species, and affect the catalytic reactions. So typically there are not only Langmuir-Hinshelwood reactions happening, but also Elie-Rideal reactions with radicals from the plasma. But also you have vibrationally excited species, which can also reduce the energy barrier for dissociative adsorption. And then, of course, you have desorption of products formed at the catalyst surface, which affect, again, the plasma chemistry. So there are a lot of interactions, and that means we need a lot of fundamental studies to better understand the mechanisms. So in my talk, I will give a few examples of such studies. I will show that actually a catalyst acts also as a plasma modifier. And I'll show this for the example of ammonia synthesis. I will also show the importance of studying the plasma discharge characteristics in plasma catalysis, because this can give a lot of insights on what is happening, and it's not just the catalytic effects. I will show this and make a comparison between dry reforming of methane and ammonia synthesis. Then I will show some modeling results for PEG-BDBD to show the change in discharge type. I will show modeling results for plasma in catalyst pores to answer the important question whether plasma can penetrate in catalyst pores or not. Then I will show some results of chemical kinetics modeling at the catalyst surface for methane non-oxidative coupling and partial oxidation. And then I will show a combined plasma and surface chemical kinetics model to show that there's not always plasma catalyst synergy, and that we might need to think more critically about what is happening. Of course, try to also provide some solutions, what is needed for plasma catalyst synergy, and also discuss a bit on other plasma material combinations. Now, this looks a lot, but actually only point 1 and 2 will take several slides. All the other points from 3 is typically only 1 slide. So don't worry if you think that I will be running out of time, because only point 1 and 2 will be a bit longer. So first, the question that catalysts can act as plasma modifiers. Here is an example of our research for the plasma catalytic performance for ammonia synthesis. And what I show here is the ammonia concentration of the ammonia produced for different cases, and also the corresponding energy consumption. At the right y-axis, we see the plasma power, and here also the ammonia production rate. So these are then the symbols. So we first look at the results here for the empty reactor. So what we can see, so these are the bars here, and we show this for 3 different hydrogen-nitrogen ratios. What we can see here is that the 3:1 ratio shows the best results, and we also see that some ammonia is formed due to the plasma, so without catalyst or without support, due to gas phase reactions. However, if we add an alumina packing, so just a dielectric packing, so now we are looking at these bars here, we see that there is again the 3:1 ratio gives the best results, and the ammonia synthesis is higher, and the ammonia energy cost is maybe a little bit lower, but not much. Actually, we should compare here with the 200 milliliters per minute. But especially we see some improvement here in the ammonia concentration, and that is because the dielectric packing causes some enhancement in the local electric field, which already has some effect. But we see a major improvement if we add cobalt catalysts. So when I'm looking at these bars here, And let's first focus on the first part, which is just the cobalt catalyst. Now we see that the 1:1 ratio is the best. We see a clear improvement, both in the concentration, so the ppms of ammonia, also in the energy consumption, which is much lower, and the production rate is much higher. So up to a factor 4 higher, and the energy cost up to a factor 5 lower. And this, the question is this due to catalytic surface reactions? Or is this because there is an effect of the catalyst on the plasma behavior? So we also compared other catalysts, bimetallic catalysts, so cobalt-based catalysts. So these are all these bars here. And we can actually see that all these catalysts have a much better performance than the empty reactor and also than the alumina packing. And the cobalt lanthanum, the somewhat better results, but not much different. And that is attributed to lanthanum being probably a structural promoter. Now, the reason why once we add catalysts, the 1:1 ratio is higher, we actually don't know yet. But we also see that there is actually not much difference between the different catalysts. It means we could as well use cheaper catalysts, because as soon as we put a metal on it, it seems to work better, but there's not much difference. Now, if we then look at the effect of this metal composition on the plasma behavior, we can see that the plasma power actually varies a little bit as a function of the catalyst. We actually put a plasma power, we apply a plasma power of 100 watts. And most systems give then a plasma power of around 65 watts, while a few catalysts like the cobalt cerium and cobalt lanthanum had a plasma power of 45-50 watts. So despite this lower plasma power, they have the highest ammonia synthesis. So they seem to be somewhat performing better. Now, if we then look at the current voltage characteristics, because it's actually very important to investigate these, because we can learn a lot about that. So we can see here that we see peaks in the current profiles, as you can see here, and these are attributed to micro discharges. We see them very pronounced for the alumina packing, not so pronounced here, and they're almost completely gone for the cobalt lanthanum and cobalt cerium. So they, as I said, these have a typical filamentary behavior, while the cobalt-based catalysts, the micro discharges drop dramatically. And this was the most pronounced here. And this is actually because we found by electron microscopy that this metallic layer, that a metallic layer was formed, and this increases the electrical conductivity, so there will be fewer micro discharges, and we have a more homogeneous plasma. And so the improvements in the ammonia concentration are actually attributed to changes in the plasma discharge properties, which affects the reaction mechanisms. And actually the reason is that less ammonia is destroyed in the plasma. So that's why I come to this conclusion that the catalysts act as plasma modifiers. There might be some catalytic effects as well, but this plasma physical effect is much more dominant. So that was the title of our paper here. So it means these catalysts can change the plasma to the desired mode, which can then be important for the applications. Now, I said ammonia is being decomposed in the plasma. This is actually an insight that we obtained from our modeling. And I show here results from a modeling that we actually developed already a couple of years ago. This was a chemical kinetics model of both the plasma chemistry and the surface chemistry. And what happened during the micro discharges, so the strong filaments, there are mainly electron impact reactions, which cause ionization of the feed gases, nitrogen and hydrogen, so into ions, also excitation, electronically excited species here as well, and then also dissociation into nitrogen and hydrogen atoms. And they recombine, forming NH, NH2, and finally NH3 by a combination of Elie-Rideal and Langmuir-Hinshelwood reactions. But we saw that during the microdischarges, most of the ammonia is decomposed into NHX. While in the afterglows, some other processes happen. The reactive species arrive from the previous microdischarge, and they will recombine back into the feed gas, or they react at the catalyst surface, again by a combination of Elie-Rideal and Langmuir-Hinshelwood reactions, into ammonia. There is still some destruction of the ammonia, but there is a net production in the afterglows. So the main takeaway of this slide is the result of our model said that the microdischarges cause a net destruction of ammonia, and that also explains why the cobalt-based catalysts, which had less microdischarges, have higher ammonia concentration. Okay, moving to the next topic. This was intriguing us, so that the catalysts act as plasma modifiers, and we wanted to study this more in detail to study the importance of the plasma discharge characteristics. And for this purpose, we compared two different catalyst synthesis methods. One was wet impregnation, where the metal nanoparticles are uniformly distributed throughout the beads, as you can see here. And the other was spray coating, where the metal nanoparticles were only at the surface. Now, SEM-EDX analysis and also other characterization revealed that indeed in the wet impregnated catalysts, the metal nanoparticles were uniformly distributed, so as a function of distance from the center, while in the spray-coated catalysts, a thin metal film was formed on top of the beads, as you can see here. Now, what does this say about the plasma behavior? When we look at the current voltage characteristics, we found that you see in the empty discharge, there are a lot of microdischarges. That's also what you can see here. In the alumina packing, that was still the case. Also in the wet impregnated catalysts, this is the case. But if we look at spray-coated catalysts, we see that the number of microdischarges has dropped enormously. I don't know whether you can see it clearly in the room, whether it's dark enough, but otherwise I think this is also quite convincing here. So this packing alters the discharge, and the spray-coated catalysts with a metallic layer make the plasma more homogeneous. That is also seen when we look at the Lissajous plots. A Lissajous plot means plotting the charge as a function of the voltage, and we see that there is a big difference in the shape of these Lissajous plots for an empty reactor compared to the wet impregnated catalysts and compared to the spray-coated catalysts. And this might be a bit too technical, but just to explain, this means that the effective dielectric capacitance increases a lot and discharging area of fraction increases. So a larger fraction of the dielectric barrier of the dielectric participates in the plasma discharge. So the spray-coated catalysts have a larger part of the reactor volume which is filled with plasma. So if we then look at the performance, and I said I would compare here ammonia synthesis with dry reforming of methane. This shows the ammonia concentration where we compared, again, the empty reactor, alumina packed, and then wet impregnated, spray coating, and we did for nickel and cobalt for different weight percentages. And this we compared with this discharging areal fraction. And if you need to know more information about that, it can be found in a paper a couple of years ago. But actually, what we can see, I already explained, the micro discharge, the discharging areal fraction says how much of the plasma is, how much of the reactor is filled with plasma, and we see a clear correlation between the spray-coated catalysts that have the highest ammonia concentration and this discharging areal fraction. So this means this higher beta means a more homogeneous plasma, more filled reactor with less micro-discharges, giving a higher ammonia concentration. And this indeed confirms again the previous modeling results that I showed a few slides ago, because ammonia is decomposed in the micro-discharges. Now, if we compare this with the performance for dry reforming of methane, again, now I show the total conversion, again, for the different cases, and I compare, again, the discharging areal fraction and the micro-discharge quantity. Now we see the most correlation between, like the best results for this empty here, which have the highest micro-discharge quantity. So the micro-discharges are now generally beneficial for dry reforming, although the effect is less pronounced. This also confirms previous modeling results that we did for CO2 and methane conversion, and we found that they are mainly converted in the micro-discharges. So the take-home message here is that the plasma discharge is strongly affected by the catalyst and also by the synthesis method. And this is something that always needs to be taken into account, not just, the synthesis method can be very important because it defines whether the metal nanoparticles are homogeneous over the beads or not. And this catalyst can strongly affect the plasma discharge, and this should certainly be taken into account. So analysis of the plasma discharge is crucial to explain plasma catalytic performance. Moving to the next topic, and I said now from now on, there's only one slide per, I think one slide per item. We did some modeling for a packed bed EBD at a macro scale to better understand the change in discharge behavior. And this is shown here for a packed bed EBD, and I only show 2 packing beads. Only half, one here, so this is one electrode, this is the other, and this is different time frames here. So we see that as a function of time, the discharge evolves. You see a higher electron density, and we see clearly surface ionization waves. So we see that the intensity, the highest intensity, is spread over the surface beads. And this was for a dielectric constant of 5. If we compare with the dielectric constant of 1000, we see here also the discharge evolve, but we see a clear local filamentary discharge. And at intermediate epsilon, so epsilon of 5 corresponds to silica, for instance. This high dielectric constant would be rather barium titanate, for instance. For intermediates, like alumina or something, you have a mixed mode. And actually, we validated these model simulations with ICCD imaging, and actually there was excellent agreement. Now, this is important because if there is surface ionization waves, a larger part of the catalyst is covered by plasma, and this will might increase the synergy. There's more contact. Now, an important question in plasma catalysis is whether plasma can penetrate into the catalyst pores. So we also developed models for this, and this was particularly some Monte Carlo simulations, and we found that the criterion for this is the so-called Debye length. And the Debye length is actually a formula that depends on the electron temperature and electron density. That's not so important, but we showed that plasma streamers can penetrate into pores when their diameter is larger than the Debye length. As you can see here, this is the electron density, and it has a maximum inside the pores. Now, this de Baeyer length at typical plasma catalysis conditions is in the order of several hundred nanometer to 1 micrometer, depending on the electron density and temperature. For instance, it would be 400 nanometer. It can be a bit less at higher voltage. So it means that if the catalyst pores are smaller than 400 nanometer, typically, like this is in the case in zeolites, obviously, the plasma cannot penetrate into the pores. This has consequences, of course, because if this can happen, the active surface area available for catalytic reactions, of course, is much larger. But if not, then plasma species might still diffuse into the pores, but also that depends on their lifetime, their reactivity. I come back to that. Moving to the next topic, we also do a lot of chemical kinetics modeling at the catalyst surface to get more insight in the underlying mechanisms. And the first example is for methane non-oxidative coupling. And I show here the turnover frequencies for different catalysts. So what you can see here, actually this was done because these were simulations as a function of the binding energy, but we can put several catalysts here and we can see a typical volcano plot here. But if we add plasma effects, for instance, vibrationally excited molecules, we see that the top of the volcano is shifted a bit. And we also see that at the top of the volcano gives much higher ethylene production now, while noble catalysts still give more ethane production. Now, if we study the effect of the plasma radicals, we see they have a much stronger effect. Now, ethylene production is favored even on the most noble catalysts. You can also see that so there is a shift in the volcano plot, and also the values are higher. So the message here is that the optimal catalyst material depends on the desired products. So yeah, typically ethylene is more desired, but also on the plasma conditions. If you have a plasma where there's a lot of vibrational excitation, these catalysts would be best. However, most plasma catalysis conditions have mainly radicals, and in this case, this can give information about that these catalysts are more desirable. Another example is here for methane partial oxidation, where we also studied the effect of the vibrationally excited species, and actually we saw a limited effect. This was only done for platinum 111. So this is in line with the previous result that vibrationally excited species had a more limited effect, while the radicals have a much larger effect. So they caused a dramatic increase in the turnover frequencies. And this could be explained because plasma allows alternative pathways, like for instance, this methoxy radical is a precursor for methanol and formaldehyde. But the coupling between methyl radicals and oxygen radicals is difficult on this catalyst. But in the plasma, these radicals and also other radicals are easily formed. And then, so you can see they are formed in the plasma. They absorb at the catalyst surface. So you don't need this coupling. You have this automatically by adsorption from the plasma, and you can then form methanol or formaldehyde. Now, I must say that this model was only for the reactions at the catalyst surface. In the next model that I will show, this is a combined plasma and surface chemical kinetics model. I show that actually it's important to combine them, and that the catalyst is not always beneficial. And there's also not always plasma catalyst synergy. And I show this as an example for the methanol production from dry reforming of methane. And I compare here these bars, plasma only, with 3 different catalysts. Actually, we compared many more, but I just illustrated here for these 3. And what I show is the total methanol production, the production at the catalyst surface, and the production in the plasma. So total in the case of the catalysts means the sum of both, while plasma only, yeah, is just total then. Now we found that in plasma only, this reaction happens, giving rise to methanol production. At the catalyst surface, also similar reactions can occur, like the adsorbed radicals can also form methanol, but this is at a much lower rate. Note the logarithmic scale here. And that's why you also see not much improvement here compared to plasma only. Moreover, this reaction forming methanol is not favored because the radicals will much more easily recombine back into methane, CO2, and also water and hydrogen, because they are thermodynamically more favorable. So actually this model told us that the catalysts act as radical scavengers. So that's why we call them anti-catalysts, because they scavenge the radicals so that the radical concentration in the plasma is lower, and then also the production in the plasma is lower. So this was, yeah, when my PhD student first presented this to me, I didn't want to believe it, because yeah, a lot of people show methanol synthesis in plasma catalysis. So I thought, yeah, we should see this in our model as well. But yeah, actually it makes sense that metals act as radical scavengers. So it's logical that radicals will be adsorbed at the catalyst. So I believe we need to rethink plasma catalysis, and maybe we need to tune the plasma conditions to maximize vibrationally excited species. So in general, I want to stress that the effect of the catalyst on the plasma discharge is very important, and we find in our experiments that the role of the plasma chemistry is typically dominant over the influence of the catalyst. So yeah, if I showed before that there's not always plasma catalyst synergy, then the question, of course, logically arises, what is needed for this plasma catalyst synergy? First of all, there is a need for better insight in the optimal catalyst material tailored to the plasma environment. If metal catalysts might not be the best, maybe we need other catalysts. Question is, would metal oxides do better? There are some papers that show that oxygen vacancies are beneficial. This is shown in this scheme here. So you would have a CO2 plasma. It would break up in the plasma in CO and oxygen atoms. If the oxygen would adsorb, they would avoid to be recombined with CO into CO2. And then two oxygen atoms can recombine as oxygen. So this can explain a better result. Another way is CO2 can dissociate, here can be absorbed, and then dissociate, and the oxygen can fill oxygen vacancies, and then CO and oxygen are desorbed. But maybe we also need to think about other materials, and here is then the question for you, because you are the Catalyst Society, and I hope you can help, and we could collaborate on thinking for better materials. But I also think that we might need to tune our plasma conditions to the catalyst needs. So if we want to use metal catalysts, radicals might not be the most suitable. If we could enhance vibrational excitation, this would be beneficial because they could lower the activation energy for dissociative adsorption. Now, the only problem is that in typical plasma catalysis conditions like DBD, radicals are dominant. So we might need to think about other plasma reactors to realize this. And then I also believe there is a need for improved plasma reactor design for better plasma catalyst contact, because we see in our experiments that the plasma chemistry is too dominant. And actually, this makes sense if you calculate the diffusion length of plasma species, which is in the order of 100 micrometer or lower. So that means that these radicals react in the plasma at a distance, at this short distance, before they can react at the catalyst surface. So it means the void space in a catalyst packing should be below 100 micrometer to promote surface reactions. And actually, we just published an opinion paper in ES Catalysis. So this is the DOI. It's online for a while already, where you can find a much more detailed discussion on all these effects. Then I don't want to end with a negative message, of course, because I believe plasma catalysis has a lot of potential, but I just think our community needs to think critically about the results and not always just believe, when we see good results, but try to understand them better. So for instance, other plasma material combinations could be very useful, like because they can give rise to product removal, for instance, sorption materials, scavenging materials, because they can avoid back reactions where CO and oxygen react back into CO2, and NO would also be recombined into nitrogen. An example that is shown already in literature is ammonia protection to avoid decomposition in the plasma. I showed by the model and also our experiments that ammonia can be decomposed in the plasma. Now, if ammonia can be absorbed inside the pores, and the pores are very small, the plasma cannot penetrate and ammonia is protected. And then after the plasma, ammonia can be desorbed, and this leads to much higher ammonia yields compared to without sorbent. And this was shown, for instance, in a paper by Rauwenhorst, and also actually for NOx synthesis, where he saw a factor 15 improvement. But also we showed in our group that a post-plasma carbon bed, so it's not really a catalyst, but it's also a solid material, can really improve the performance because the oxygen produced from CO2 splitting can react with the carbon atoms and give much less recombination with CO and give a much higher net CO2 conversion. And also the unconverted CO2, if the carbon bed temperature is sufficiently high, can give rise to the reverse boudoir reaction, giving rise to further CO increase. And we published 2 papers about this in this year. And this figure summarizes a bit the results. So here we show the energy cost as a function of CO2 conversion. The blue data points are just CO2 without carbon beds, and the red data points are with carbon beds. And the numbers are different references. That's not so relevant, but you can clearly see that both the energy cost is lower in CO2 with carbon beds and the conversion much higher. And the results that we obtained were number 1 and 2 here. So they're quite low energy cost. And also post-plasma catalysis, where the hot plasma gas can thermally activate the thermocatalyst, although there is not strict synergy with radicals, for instance, a reactive species. I believe there is a lot of potential here. And that brings me to the conclusion. I think plasma catalysis has many knowledge gaps and many challenges. For instance, also in correctly measuring products, because some groups detect a lot of methanol, but when this is measured offline, it can give a wrong impression because it's difficult to compare this with online analysis. And so if you do it online, we are trying to compare that in our group. The online detection of methanol is much, much lower. And of course, if you compare offline, which is based on accumulation, with online, that is that gives different results. So I think there are still challenges in our field, but there are also huge opportunities, and there is a need for better understanding by both experiments and modeling to tune the plasma to the catalyst needs and vice versa. And for this, we need more collaboration between the plasma and the catalysis community. So I want to shake hands. I'm, I think, Mrs. Plasma, and you are also Mrs. or Mr. Catalyst, and I would like to collaborate. So, and actually, for more information, I also want to refer to this recent Nature comment paper that was published last week, so where you can also find a bit more information on challenges and also opportunities of plasma more in general for rectification of chemical reactions. And with this, I would like to thank you for your attention.
Well, thank you, Annemie, for a really fascinating talk. So, are there any questions from Mr. Catalysis? One over here.
So we've had a question online.
Oh, yes, please.
Which is, do you have any data for the benefits and advantages of plasma and ionic liquids for the
Comparison plasma and ionic liquids.
Yeah, to be honest, I'm not working on ionic liquids and I don't know the field very well, so I cannot really judge. But yeah, what I can say is, yeah, plasma is of course very reactive, has these radicals and these excited species, which can work in nice synergy with the plasma, with the catalyst, but not always. And I believe actually, especially vibration excited species would be beneficial. But yeah, more research is needed, and plasma could also have the advantage that it's compared, for instance, to electrocatalysis or photocatalysis, that it can happen in the volume and not just, yeah, let's say two-dimensional. But again, yeah, there should be a good contact, as I said, between plasma and catalyst.
Yeah, we could take one more quick question from the back.
Hi, Annemie. Thank you very much. It's Chris Hardacre here. On your methane coupling, where you were showing the different metals, there's the plasma-only part, which gives you large amounts of oligomers and coupling products there. How do you stop the oligomerization of the methane and only get selective ethylene, acetylene, or whatever?
Yeah. So this is a very important question. In the plasma itself, you will not selectively produce only one hydrocarbon, because plasma is so reactive. Now, typically at DBD plasmas, so the cold plasmas, you typically produce mainly ethane in the plasma, but as I showed, at the catalyst surface, it can change. Now, if you have warm plasmas, we do a lot of research also on warm plasmas and thermal plasmas, you mainly form acetylene, and then with post-plasma catalysis, it is very well possible to have post-plasma catalytic hydrogenation into ethylene, and then that seems to be quite selective. I hope that answers your question.
Yeah, thank you.
Annemie again, for a really fascinating